I've got water drawn up on here. All right, so this is the second part of our determination of different molecular shapes. So I've got water here. Now in this case, the central atom has got lone pairs. Since they're not bound to atoms, all of these lone pairs are going to be considered electronic domains only. And we don't include them for determination of the shape of the molecule. But that doesn't mean that they don't have an important part to play in the shape. Okay? So what I'm going to do here is I'm going to change the order. And what I'm going to say is, I'll start with electronic domains and atomic domains over here. And then the overall shape here. Okay? So in this case, with the water molecule, I have two atomic domains. And I'll represent those in red. Okay? So I've got atomic 1 and atomic 2. Okay? Let me grab green over here. We'll use green for this other one. For lone pairs, I've got electronic domain 1 and electronic domain 2. So the number of electronic domains I've got is 2 plus the 2 bonds, because in this case we're counting those electronic domains. Okay? So 2 and 2. So electronic domains here is going to be 4. The atomic domains in this case are going to be 2. Right? Because I've only got those 2. So my electronic domains in this case are going to be what? A 4 shape. What is it when we have a 4 shape? Okay? If you think about it, the oxygen is going to deform so that the hydrogens are going to be as far apart from each other as they can be. And the lone pairs are going to be as far apart from each other as they can as well. So, if you can think about it, the shape is going to be about 109.5 degrees, and the shape here is going to be tetrahedral as well. But the tetrahedral domain is only for electronic. It still has 4 points in shape, or 4 points in space, and that's going to determine what the overall shape is. But I only count 2 atomic domains. So for overall shape, I take the lone pairs away. And what's the overall shape of water in this case? That's right. It's not linear. It's kind of bent. And that's what it is. It's a bent shape. Good. All right? Now, what about something a little bit more complex? Suppose I have NH3. Okay? NH3 has a lone pair on the nitrogen. So before drawing the structure, what I want you to do is I want you to determine the number of atomic domains that it's got and the number of electronic domains that it's got. Go ahead and hit pause, write down a number, and we'll see if you guessed correctly. It's got 3 atomic domains. And it's got 1 electronic domain. Okay, but we count the electronic domain in with the bonds. So the number of electronic domains is going to be 4. And what we have when we have a 4 electronic domain structure. The electronic shape, the electronic dimensions is going to be tetrahedral. Okay, just like methane. And what am I going to do for the atomic domain? The atomic domain is what? I've got 3 here. Okay? So since I have 3, I erase what the overall shape of this is going to be. So now let's draw nitrogen and its bonds. So I've got 1 hydrogen here. I've got a hydrogen coming out of the board at us and a hydrogen going away into the board away from us. And I've got 1 lone pair, which is sticking out up here. The bond angle here is still 109.5 degrees because it's still a tetrahedral shape. Okay, does that make sense? Good. So when I look at the atomic domain, I have to erase the lone pair. So my lone pair goes away, and what I have now is that weird shape. And it's not really a triangle because it's sort of raised. that lone pair disappeared, which means that the central nitrogen is an exposed point. So if I were to draw this at a point, that would be my nitrogen. It would come down to 1 point at that hydrogen. It would come sort of away or towards us there and have 1 in the back. So if you look at that shape, it's kind of a pyramid shape. It's not as glorious as the tetrahedron, but it is a shape. And it's a pyramid, and it's got 3 points down here at the end. So this one we define and say that this is a trigonal, triangular pyramid. Okay? So let's look at one more structure. Okay? Erase nitrogen here for a second. And what I'm going to use here, HF. But this time, instead of looking at the hydrogen, I'm going to look at the fluorine. So I'm going to look at that guy. If you look at fluorine, fluorine has got 1 bond to hydrogen. I'll put this up here. And all the other lone pairs that are around it are going to be in these shapes. Okay? So what's the electronic domain or electronic structure around fluorine? Still got 4 electronic domains. So guess what? It's still a tetrahedron. Okay? And how many atomic domains does it have? It's only got 1. It's got that hydrogen. That's the only atomic domain that it's got. So as a result, there's 1 atomic domain. So what's the shape around fluorine? Only 1 atomic domain, 2 points make a line. So this is linear. Although my tetrahedral shape in the electronic domain does have an implication of the shape around fluorine as far as repulsion goes. Okay? So those are the basic second row elements. What happens when things get kind of crazy? We get into weird metals and hypervalent structures. Let's look at the next video and do that.